So gas laws. So it's still the same notes. I think I posted the review, right? Is the review there for Thursday? Hopefully. And the biggest key, which if you just did the study set, then you should be pretty good with it. But why gases are special is that they have very, very weak intermolecular forces. So they're not around each other. They're always bouncing around. And we just went through all the variables. So I think we did the first 4 pages. We did 5 pages. We did 6. We're at the bottom of the page 22. So there is a question about partial pressures on your worksheet today. But it's pretty easy. And this is a formula that they often give like online and stuff. This actually comes from, if we did, remember P1 V1 over T1, and if we add in the N, if we put that in there, so it's that basically equals R. So it's all coming from PV equals nRT. So it's pressure times volume over NT. But you just keep setting them all up to each other. So P1 V1 equals P2 V2 over N2 T2. You don't have to write this down, but it can help see where the formulas are coming from. There is what they're doing here in this formula is they're just leaving off the volume and temperature, and then they're rearranging it. And instead of saying ones, they're calling it A. So NA is N1, P1, and N total, P total. So if you rearrange this, you actually do get NA over PA, which over here I'm calling ones, equals N total over P total. So what this has to do with partial pressures are actually really simple. Is that you can add up pressures. So you can add them, and this is how we write it, is like that. We write the capital P, and then that's like a subscript thing, total. And so in this room, there's oxygen, nitrogen, CO2, argon. And so we can just add all the pressures, and these are called partial pressures. And they all add up to the sum of the total. Moles are also additive. So you can add all the moles up and get the total moles. And so most gases, of course, are mixtures, which would make sense. All right. So when you do the one on the worksheet, this is the formula. And again, if you're solving for pressure, you would just flip it so the pressures are on top. And this picture over here is trying to show you if you have this and you have this, then when you combine them, you have twice as many moles. You have the combination of the moles, so you're going to have more collisions if the volume and temperature don't change. That was something we didn't do. We didn't explain if our answers were right. So, all right, so let's go through this. You have 1.0 liters of nitrogen. So several people came early and worked on their worksheet during office hours. Diatomics: nitrogen, oxygen, fluorine, chlorine, hydrogen. So a lot of the gases are diatomic. So nitrogen as a gas is N2. And this is at STP. So what is STP? Anybody?
Into temperature pressure, so 1 atm and 273.
Yeah, so 1 atm and 273 K. So this is all about nitrogen. So I like to bracket it like that. And then it says we're going to take 500 milliliters, do a different color of neon. And this is at 212 millimeters of mercury, 25 degrees Celsius. So there's a couple changes that are happening. So if you look, the volumes are not going to add up to 2 liters. So what you're going to have to do is you're going to have to figure out the moles of the nitrogen. I think the hardest thing people have with partial pressure is every question's different. If in doubt, you can always do PV equals nRT. You find the moles of each. So that's going to be your step 1 and step 2. Step 3 is you're going to add your moles together. And that will give you your mole total. And then step 4 is we do PV equals nRT again. So we'll put the total moles in there. And we'll put the total volume, the final, in there and solve for pressure. Oh, and the final temperature. That's given in the problem. So I'm going to pause. I'm going to give you guys a chance to play with that. I didn't give you much room, but at least try to find your moles. This is going to be using PV equals nRT for both step 1 and 2. So try it. See what you get. I'm going to pause this. I'm going to go ahead and walk through it for people who are stuck. So again, the hardest part about partial pressure is every problem's different, but it's just gas laws, and it's just that we have a mixture of nitrogen and neon. So you can always PV equals nRT. If in doubt, use that formula. And it just takes practice, and that's what the next 2 pages you should have. I'm missing a page. All right. So PV equals nRT. And we're going to use, and again, STP means 1 ATM. So that's the hardest part, is that people don't realize the nitrogen, it's giving you a pressure. So we just plug in and solve for N. So we'd have 1 ATM times its volume, 1 liter, over R times the 273. If you're right, you have to make sure you divide by both of those, and we should get that number. We would state again our formula here. So PV equals nRT. So our pressure, right, will divide by RT. You do have to change your pressure. So you have to divide by the 760 to get to the ATMs. You do want to show me that step. The volume, we do need to change it to liters, so 0.5 liters, and then over R times 298. Again, always in Kelvin. And that should give you that many moles for the nitrogen. Again, this is how you write it. So little n is always the symbol for moles, and then we put a subscript, nitrogen, or little mole, little n, neon. Oh, by the way, that was the other thing. So I've had 2 entries for naming my new pet in the backyard. My mole holes have increased. I think there's more moles. I think he has a friend. So Damon gave me the name of Mozart. Somebody last night gave me one that might be yours, Damon. It's all right. You get a bonus point. You should all give me a name. And theirs was Maleficent. So if you know the movie Maleficent, so that was from Sleeping Beauty, what's called, it's the misunderstood that everybody thinks moles are evil. This mole is aerating my garden. He's aerating a little bit too much. There's a lot of worms in my garden. That's good. All right, so we would add the 2 moles up. So state your formulas, number your steps, and we would add these up, and then we would plug in. So our pressure is what we're solving for. So our total moles, our N total, whatever that number is of the 2, times our temperature final is our 298 Kelvin, and our volume final is the 2.0 liters. When you do that, you'll get to ATMs, which I got like 0.615 ATMs. And then you would have to show me the step that you multiply by the 760. I didn't actually indicate what unit, so you were perfectly fine to keep it as ATMs. Questions with that? All right, I have to find my next page. There we go. So now we're going to go through some theory stuff. One of the biggest comments, and that's why we're doing a review, there's a lot of, so about half of the midterm is math, and then about half of it is words. It is all show your work. or circle an answer. So we'll do a review. So intermolecular forces. So remember NOF, that's where the NOF comes from. So nitrogen, oxygen, fluorine. All right. So these are the assumptions for the kinetic molecular theory. So KMT, kinetic molecular theory, is a theory about gas laws. So the mathematical part about gas laws, those are laws. Those are our primer, those are our building blocks to figure out things. This is all theory, theoretical, that make gas laws work. And the question I have there is really important, so I'll ask it again. What is different about a gas? What's special about a gas that's different from a liquid and a solid? What makes a gas a gas? IMFs. That's like our key to this whole midterm is intermolecular forces. Gases have very weak intermolecular forces. In fact, there is an assumption, which is step 4. So elastic collisions are if you had perfect pool table that was frictionless. So you had Galileo's frictionless pool table and the billiard balls, they would just bang off of each other and keep moving. And so the assumption is actually that there are no intermolecular forces. When I said weak, it is like very, very weak. Intermolecular forces, so there's no stickiness. So they don't get stuck together. They're always moving around, and that's what this picture here is trying to show. The other big piece is what number 1 is. So they expand. They're expansive. So in case you also don't know, we've walked through the chakras over the past couple of weeks. So in the ancient yogic philosophies, our chakra system is we have these points of light within our body that actually correspond to the hormonal endocrine system. But the gases is the heart chakra, air is the heart chakra, which makes sense because it's expansive, that we're always expanding into love. That's the only thing that matters. That is the big thing that's different about humans, is we have that capacity for compassion and love. And that's what we're supposed to be doing. So if you're ever in doubt, just pick the most loving choice and follow that. So crazy yoga teacher told me that. That's why I kept studying with him for 3 years, because he was right on that point. Everything else he was a little bit crazy about. All right, that's probably what you're thinking about me. So just follow the path of love and you'll be okay. And wear enough. And name my mole. You can even make Damon, I'm going to say this because Damon's going to do it. You can even knit a hat for my mole. You make him a little enough. I don't know. Yeah. All right. They're very misunderstood. They don't have eyes, apparently. They don't need them. We probably don't need them either. All right. So this step, that the space in between the molecules, the space in between the gas particles is huge. And so we assume that the particles themselves aren't occupying any space, so you can compress them, which is something that makes them very special. Now, a lot of you are going into engineering and you can compress liquids. It's like an infinitesimal amount. And so that's totally different type of math. This is an interesting number. We can condense the air in the room, right? We can do the Star Wars. It's Star Wars Day, right? May the Fourth be with you. So all of our walls are going to condense in on us and squish us, unless we have Chewbacca there to grunt and hold the walls, which didn't really work. But 99.96% emptiness in the room. Every atom in your body is 99.999999999 19 nines before you get to another number. So it makes you really think about what's going on. And it's not in the atom, that emptiness is where everything's happening. So ponder that about the emptiness in the room that we all think about as empty space. Is it really empty? Or is it our perception of it? All right. The other thing that I mentioned earlier, and it's why we can actually step 2 and 3 is why we use Kelvin. They are in continual motion. And so Newton actually said things move in straight lines until they run into something. This is actually kind of a cool fact. You don't need to know this, but the oxygen moving around in this room, I had to type it out because I always forget it. They're moving at 1,000 miles per hour. Isn't that's like really impressive. And so every second there's over 5 billion collisions. Like there were just 5 billion. There were another like 20 billion. So two terms I do need to mention, because we'll see these, is diffusion and effusion. Does anybody know what either one means?
Diffusion when it spreads out.
Yeah, so diffusion would be like if we were in the classroom and I opened a perfume bottle, the first row would smell it first and the next row, and so they're going to spread out. And they do take up all the space of the room, and so they're going to diffuse. Effusion is it's moving through a small hole. Effusion is what they did in the Tennessee Valley during the Manhattan Project, and that then goes, and so the smaller gas particles are going to get through that hole more likely. And so it was how they isolated more uranium-235 from 238. But both of them have to do with the same thing, is that things are spreading out, and it leads into number 3. That the kinetic energy, that little fish sign, is proportional. That kinetic energy is proportional to temperature. So as you increase the temperature, you increase the kinetic energy, which means everything's faster, or you have more giggles and jiggles and wiggles. It's more fun talking about them as giggles and jiggles and wiggles, because you really can't talk about giggles and jiggles and wiggles without smiling. Try it, but it's kind of hard not to smile, and we need more smiles. So if you increase the temperature, you have more giggles. What this one says is it is dependent on size. So that line there means average kinetic energy. So the kinetic energy of every particle is going to be different, but on average, they're increasing in their giggles and jiggles as you increase the kinetic energy. The formula for kinetic energy, so I'm going to go into this, but is 1/2 mv squared. So v is velocity. When you take physics, this becomes ingrained in you and you never forget it for the rest of your life. What they did is they then took gas laws and put this all together, and they come up with this lovely formula here. We're not going to work with that. We're going to work with it theoretically. This v is the velocity. The line is on it because everything has slightly different velocity, so it's an average velocity. You square it and then take the square root, because velocities can be positive or negative. So when you're going backwards, you have a negative velocity. So they square it and take the square root. That's what RMS means. So RMS means root mean square. I think I may have gotten that backwards. Velocity is always positive, but speed can be positive or negative. But root mean square means it's always a positive number. So the RMS speed is that if you're at a higher temperature, things are moving faster. What this is doing is it's also comparing it to capital M. And so what this is saying is it's an inverse relationship. So T's on top. So as you increase temperature, you're going to increase the giggles. But as you increase M, the grams per mole, you actually decrease how fast you're moving. So the velocity, or the RMS, root mean square speed. So if you see that RMS designation, don't let it scare you. It's an inverse relationship. And this has to do with the whole effusion, that the smaller ones are going to get through that hole faster, and they're going to spread out faster. So on the periodic table, noble gas, helium's going to be the fastest moving one because it's the smallest. I call this the Thanksgiving philosophy, that on Thanksgiving, when you start eating more and more and more and more and more, and you become like radon, or orgasium, I think his name is our next one here, is you you start moving slower. So the larger ones move slower. So they're slower. All right. This little thing also we're not going to do anything with, but comment on it. So van der Waals equation is, he took into effect the idea that the particles do take up a volume. So the size of the particle. So he's saying the atoms do take up some space themselves, not the space in between them. And so you have to always subtract that out. So the n is the number of the particles, the moles, and then the b is the size of the actual atom. So the atom or molecule. And then over here, the whole idea with pressure is it's assumed that pressure is collisions, that everything's colliding perfectly. He's factoring in the IMFs, so that there is always some stickiness, but it's really minute. We used to do a lab with this, but I was like, before many of you were born, that was like 2 decades ago. Yeah. All right, if you decide to study gases, you'll get to learn this formula in more detail, but that's all that was. All right. So what this is we're going to just hypothetically say something happens, and then we're going to explain why the other change happened. So you have a cylinder that has a movable piston. So you basically, something's in here, and this piston can change the volume, so moving in and out. So it's asking what would happen to the pressure inside as we make each change. So if you double the volume, temperature is constant. What happens to the pressure? Anybody?
It decreases.
Yeah, so it's going to go to 1/2. So the question is, Max, I get your name up on the board. Why?
Because you have more room with the same amount of molecules.
So there's more space, same giggles, right? So same kinetic energy. So you're going to have fewer collisions. So when I ask, because I will be asking this like on your study set and then on the exam, when I ask you to explain why, I'm not wanting you to tell me, oh, because they're inversely related, that when volume goes up, pressure goes down. I want you to explain why that happens, that if you're giving them more space, they're not going to collide into each other as much. It's kind of like what's happened in this past year. We all give each other more space, and so there's not as many collisions. Yeah, and like what he said, so it's same kinetic energy and same number of particles. So we haven't changed, or the same number of moles. All right, so if we increase the temperature by 3-fold, so a 3-fold increase in temperature, what's going to happen to the pressure this time? Volume is constant. So somebody else. Yeah, 50-50 chance. They're going to go up or down. But you have to ponder how to explain it. So temperature is, go ahead.
I want to say it's going to go down.
No.
When temperature increases, the pressure will move up. It'll increase.
So an increase in temperature means there's more giggles, more kinetic energy. So you can say giggles, you can say they're moving faster. It's kind of up to you, and I asked for the explanation. When you take Dave Faust's class next year and you say there's more giggles, he might not understand what you mean, but I will understand it. And for you to giggle a little bit while you're taking your test, that's a good thing. All right. You should all do it next year in Faust's class. That would be great. We're gonna like make Faust start talking about giggles and jiggles. He's got like the greatest smile in the world too. So if you have more giggles, you're gonna have more collisions. And we all know that, because when you start laughing, we all start moving around and jiggling. So you're going to increase the pressure. And it is, if you're in Kelvin, it is going to be a linear increase. It is a direct relationship. And that is because it's the same space. So if the volume was constant, we keep you in this room. We didn't add any more people, but you start laughing. You're going to start, I mean, these are serious giggles going on. This is a 3-fold increase in the temperature. All right, so those weren't too bad. There is another way to think about it. And I'm going to mention this. And for some people, they get it from just thinking of the giggles, the collisions, the space. If you have any trouble with that, I'll do it down here. You can always go back to PV equals nRT. And I'm an October birthday, so I'm a Libra. So I always think of, I have to have everything balanced. It's an issue Libras have. And it's really great because next term we start with equilibrium. So anyway, that's my attempt at making a scale. That's why I had to stay in school and was a good student, because my drawing skills, I can draw a stick mole. I just want you to know that, with a knoth. If they're on the same side of the scale. So if we increase the volume to keep the scale balanced, if nothing changes on this side of the scale and this increases, then that has to decrease. So if they're on the same side of the equal sign, if one goes up, the other has to go down. All right. If they're on opposite sides of the equal sign, if one goes up, the other side goes up. So when they're on opposite sides, they will go the same way to keep it balanced. So it's something you can ponder. That little trick sometimes helps a couple of people who have trouble more with the words. All right, so we have 2 flasks. They have, so one's going to have argon and one has neon. They have the same volume, so you can make up whatever volume you want. You can say 1 liter, so they have the same volume. Or you can just write the same volume. And they're both at STP. So same temperature and the same pressure. But one's argon and one's neon. So if they have same volume, same temperature, and same pressure, they have the same molecules. Because if PV equals nRT, if PV, T, and R are the same, then the N's the same. So, all right, if everything else is the same, but something must be different, and that would be the mass. So density is the PM equals DRT. Molar mass is different. So whichever one has the higher molar mass is going to have the higher density. Everything else is the same. The collisions are the same. So the one that must be the larger size particles, so larger particles or larger atom, is going to be, it's going to, it's going to be more dense. It's going to have more mass. And because everything else is the same. If something else was different, that would be different. So that would be the argon. All right. So on C, which one has the higher average kinetic energy? So anybody?
Would it be neon?
No. Why were you thinking neon?
I accidentally looked up kinetic energy and velocity on accident.
Yeah, so be careful with that. Kinetic energy is proportional to temperature. They have the same temperature. So I'm actually really glad you mixed those up, because that's a huge help for the whole class. They have kinetic energy is temperature. They have the same temperature, so they have the same kinetic energy. They have the same giggles and jiggles. So this question drives some students crazy, because 2 of the answers so far out of 3 came out the same. On D, it's going to be different. So if you had a pinhole, this is effusion. just our new vocabulary word for tonight. Which one would empty faster? And it would be the smaller molar mass, higher velocity. So it's like the Speedy Gonzales, the little mouse, my little mole, he's going to get through that hole faster than you and I because he's little. And so neon is going to be that. So this is an inverse relationship. All right. So questions on that page. All right, if you look at the next page, we're going to do some practice problems, which will help you. The answers are there. I'm going to pause us. You can take a 10-minute break, or you can try some of the problems. Paying attention. All right, we're going to try that again. So label your variables. What I just said, we'll say it again with my recording, is when I ask what's the volume, sorry, I have to be in the picture. It asks the question at the beginning. So V1 is your unknown, and there's our P1. These two go together. State your formula, rearrange, plug in, and solve. On the next one, what is the temperature? So I'm going to call that T1. So V1, and that's supposed to say millimeters of mercury. So next Tuesday, our celebration day, I will be on Zoom. So if you have questions or something. And so this is my V2, T2, and that's millimeters of mercury. So we're doing, you don't have to copy this right now, but P1 V1 over T1 equals P2 V2 over T2. I don't recommend that you actually write it like that. I recommend you have a sheet with your formulas on it, and you go, well, this is the one I want. You leave the N out because there's no N in this. But I wouldn't write it like this. I would write it T1 on top. If you're solving whatever variable you're solving for, that is the variable you want on top. Because otherwise you guys rearrange it incorrectly. And I'm going to solve for T1. So my P1 V1 will move to the top. Temperature has to be changed to Kelvin. So you're going to have to add 273, and then at the end, you'll subtract the 273. So ask the question again. Why does it have to be in Kelvin? I don't know if Maddie's there to answer again. Anybody else? Anybody remember? Why does that have to be in Kelvin?
Because of the motion of the gas.
Yeah, so gases are in constant motion, and Kelvin has that concept in there. Another question I have for you is, this is in millimeters of mercury. Do we have to do that step where we change it to ATMs? And several people are saying no. If you're doing the ratio problems, like these two, as long as the pressure is the same unit, temperature though has to be in Kelvin. All right, and then you would get my answer. So I think that a lot of students, when they do this one, get negative 54. As long as we're in the ballpark. So negative 54 degrees Celsius, negative 57, I don't remember, and I'm not going to go through punching it in right now. STP means 1 ATM, 273 Kelvin. We're looking for density. So PM equals DRT. State your formula. So again, this is one formula we're using. We're solving for density, so we'll divide by RT. And the other comment, you need to know this for the worksheet, nitrogen is a diatomic. So the molar mass of nitrogen is not 14.01, it's going to be 28.02. So the molar mass, molar mass is from the periodic table. And the pressure R and T, you know, and units. You got to have units. You've got to show units. You have to state the formula. And again, you can make a list, or that's kind of what I was doing here. All right. The next one is just asking what's the volume. It gives us a mass. Oxygen again is O2 and STP. Now, there's a little trick you may find online about when you're at STP, and if you know that trick, you can use it. I stopped teaching it because There's just too many extra pieces of information. It doesn't ask for density or molar mass. It doesn't give me 2 of anything. So we're just going to do PV equals nRT. The 216, that is going to go into the N. So your N is going to be 216.8 grams of O2, and then 32 grams to 1 mole. Or sorry, 1 mole, 32 grams. So again, I like to show it all in my setup. So then I would have R, and then I would have my temperature, which is 273 Kelvin. And R, you can just write like that. And then we're dividing by the pressure, which is 1 atm. So I like to do it all in one setup, or you can make a list over here and show your conversion of grams to moles. And again, STP just means that 1 atm. Any questions for that page? I'm motivated to be done at 7:30. All right. So one more page. These are a little bit more challenging, but let's go ahead and walk through it. Quick comment for you. Your next worksheet is more challenging. So you're going to kind of see that as a theme. The first worksheet in the stuff isn't going to be as challenging. It has problems just like this one. So and the next study set, the first page has more challenging problems than the second page is the theory stuff. Do the best you can with the theory stuff, and then know that we'll go over it. All right, so the silane must be this, because it's not the O2 and it's not the H2O, and this is silicon dioxide. So this is the silane. You could also Google it and you should get SiH4, or you would come to Zoom next week and say, hey, is this what it is? So we have, I'm going to make a list under it. We have 5.55 liters of this. We're at 333 millimeters of mercury and 22 degrees Celsius. And then it reacts with the oxygen, and the oxygen is 444 millimeters of mercury and 33 degrees Celsius. And it wants to know what is the volume. So if you're in doubt, you can always do, I'm going to give you the long way to do it, and then I'm going to show you the shortcut. You can always do step 1, PV equals nRT. Solve for moles of the SiH4. Step 2, I'm going to show you a much easier way to do it though. So you can just like sit back and listen. You do your mole to mole ratio. So you have your so many moles of the SiH4. And then you guys know how to change it, right? 1 mole SiH4 to 2 moles of oxygen. This gives you your moles of oxygen. And so then you would plug it back into step 3, PV equals nRT. And this time you would use this information and this moles. So you would have to number your steps, have everything labeled. This little subscript designation is used with pressure and moles. So N of O2 or N of SiH4. There's an easier way to do this. We are solving for volume. You do pressure of the SiH4 times the volume of the SiH4. You can call them ones if you want. Over N, you do have to factor in N times T of the SiH4 equals P of oxygen, V of oxygen, N of oxygen, T of oxygen. So we do the combined gas law. We do all of them. You have to factor in the moles if there's a balanced equation. So we don't have to do the conversion. We do have to change these to Kelvin. These we can leave in millimeters. We're solving for V. So my question, and if you see this, this is awesome, or I'll show it to you. What is the N of these? Well, it's from the balanced equation. The coefficients, mean moles. So for the SiH4, you would have, this would be a 1. And for oxygen, this would be 2 moles. And so you can do the whole thing in one big setup without having to break it into these 3 steps. So the stoichiometric numbers are the N, the moles. So this would be 1 mole, this is 2 moles. So it's a really cool trick that works sometimes. And you can play with it on the study set and see if it works out for you, or play with it with this one. Any questions? All right, I'm gonna move on. Next one is a partial pressure one. It's just, I think the thing with partial pressure is I had a student, she had always had 102% in the class, and this was the only question she missed the whole term. And she just said, I don't know why I don't like partial pressures. I think it's just there's a lot of information. So we're trying to find the pressure of the hydrogen. And again, that's how you write partial pressure. And so we have a mix. We have 1.5 grams of hydrogen. We have the oxygen. We have the argon. We have the volume. So volumes, all the gases are mixed together. All the gases are taking up all the space. So whatever the volume is, it works for any part of the component. It's just they each have their own set of they each have their own moles. And the temperature, they all have the same average kinetic energy because they're all mixed together. So 88 degrees Celsius, and we change that to Kelvin. This is extra. We do not need that information. You don't need to do anything with those because it doesn't care about them. It's just asking about the hydrogen. And I think that's one of the hard things. Today, you do need both pieces on the worksheet. So you would just change this to moles of hydrogen. We're going to do PV equals nRT. Solve for the pressure. We did last term, a cubic centimeter was the same as a milliliter. Remember doing those? I'm going to show you because we're not in milliliters, we're gases. Gases take up a lot of space. So a cubic decimeter is the same as 1 liter. So this, we would have to do that. A meter is 10 decimeters and cubit. So you do have to change it into liters. So a cubic meter is a kiloliter. So you want to be in cubic decimeters. Keep that in mind because on the worksheet, I think there's something where it's in cubic meters. And so you have to do a conversion to get to cubic decimeters. And then, of course, here you just add your 273. Hydrogen's a diatomic, so grams to moles. You guys know how to do that, right? 2.016 grams to 1 mole. And again, you can do it all over here in the list, or you can do it in your setup of PV equals nRT. I think the biggest thing with this one is there's this extra information. That's why I'll be on Zoom on Tuesdays, so if you have questions. Yeah, and please study. It's going to rain Thursday and Friday, and then the weather becomes phenomenally beautiful. It's going to be like 70s for a week. Study, because it's going to be beautiful on Wednesday, the day after your celebration. So everything's going to be fine. All right, we're going to do one more. And actually, if you study, then it's not going to take you 3 hours. And then you'll get done early, and then you can go see the sunset. I'm giving you percents. So we have 46.2% carbon, 53.8% nitrogen. And then it gives us a temperature, right? So we have 25 degrees Celsius, 750 torr, 1.05 grams, 500 milliliters. And it wants to know the molar mass. So we can do PM equals DRT. Solve for the molar mass. Density is grams per liter. So I will plug this one in. So we would just take the 1.05 grams and 500 mils is 0.5 liters. Our temperature is 298 Kelvin. And then the pressure in torr. So we need it to be an ATM. So you're going to divide by the 760. All right, that's going to give you your molar mass, the 52. Then once you do a molecular formula, so I just remember empirical formula. You have one of these on the next worksheet. So you change your percents to grams, then you go to moles, then you divide by the smallest. Just remember doing this last term. And then you make them into whole numbers. So it's going to come out as a 1-to-1 ratio as CN. To go from this to get to the 2-to-2, we would add this up, that you would have, this would be 26.02 grams per mole. And we'd see how many of these fit into the molar mass. So you do the molar mass divided by the empirical mass. So 52 divided by 26, and that's where the doubling comes in. Yeah. So it's just showing you how things that we learned from previous terms could come, how it all applies together. Some books actually teach gas laws first, because that's where the concept of moles and molecules came from, and then build from there. Some of the original chemists, that's what they worked with, was gas laws, because they have clear laws. Questions on any of these? And again, do try them. Do your study set. You can always do these this weekend if you're feeling like, but this is me giving you more practice to do. On the lab, so it's lab 6, even though it says lab 5. So this week's lab, one of the 3 activities, you have to pick 3 activities. One of them is gas law problems. So it's just to give you more practice. And I'm going to go ahead and stop